The plasma membrane plays a key role in the behavior of cells, which includes cell-cell communication, adherence to other cells or structures, cell movement and migration, access to nutrients in the cell microenvironment, and immune recognition. Receptor interceded. The extracellular material is disguised in the wake of the official with an explicit cell receptor. Pinocytosis. The cells take up liquid and any particles contained in it from the encompassing medium. Inflammatory barriers. Tissue harm by wound or attacking pathogens instigates a perplexing grouping of occasions known as a provocative reaction. Atomic segments like lipopolysaccharides trigger a provocative reaction by official with a cell surface receptor. Aggravation has 4 cardinal signs: rubor or redness, tumor or swelling, calor or warmth, and dolor or torment. Bumblebee sting causes serious agony, aggravation and hypersensitive response through interceded hypersensitivity. Melton is a poison found in the honeybee venom. It is an amazing trigger of phospholipase A2. It is a film-restricting protein that is engaged with an acting phospholipase in the layer. The conceivable target phospholipase that is initiated by Melton is phospholipase A2 to produce arachidonic acid. Acute phase proteins. Heterogeneous group of plasma proteins predominantly delivered in the liver as a consequence of a microbial improvement. They incorporate C-responsive protein, serum amyloid protein A, and mannose-restricting protein. Cytokines like IL-1, 6, 8, and so on discharged by macrophages upon the actuation by microorganisms animate the liver to quickly deliver intense stage proteins. These proteins expand the initiation of the supplement framework and the opsonization of attacking organisms. Cellular defenses. Many particular cell types like neutrophils, macrophages, monocytes, and normal executioner cells partake in inborn host safeguard components. When a pathogen avoids the physical and synthetic obstructions, these particular cells assume a significant job in insurance. Phagocytosis is a principal defensive instrument completed by these cell types: neutrophils, macrophages, monocytes, and dendritic cells. Oxygen-dependent killing. During phagocytosis, a metabolic procedure known as respiratory burst happens in inactive phagocytes. It results in a transient increment in oxygen utilization by cells. Actuated phagocytes create various dangerous items, for example, receptive oxygen intermediates and responsive nitrogen 2 intercede, which have intense antimicrobial action. Oxygen-independent killing. Activated macrophages additionally combine lysozyme, defenses and different hydrolytic compounds or cytotoxic peptides whose degradative exercises don't require oxygen. It is otherwise called acquired or specific immunity and is started by acknowledgement of a remote antigen and specifically taking out the perceived antigen. It becomes an integral factor just when there is an antigenic test to the life form. Ability to recognize among antigens is known as antigen explicitness. Once the resistant framework has perceived and reacted to remote molecules, it can react to a similar antigen in a progressively fast and uplifting way. This is immunologic memory and the reason for long-haul invulnerability to numerous pathogens. Immunological memory. The capacity to explicitly perceive billion of interestingly various structures on remote antigens diversity. To perceive and react to outside particles, as it were. On the off chance that this normal for insusceptible framework comes up short, it offers a sense to immune system sicknesses. Versatile invulnerability for explicit pathogen can be created through characteristic group by getting contamination or artificially through vaccination, self or non-self acknowledgement capacity. The humoral response incorporates B cells that see antigens or pathogens that are streaming in the lymph or blood. Antigens bind to B cells, interleukins or Th cells co-animate B cells. A significant part of the time, both an antigen and a co-trigger are required to order a B cell and begin B cell duplication. B cells increase and produce plasma cells. The plasma cells bear antibodies with the unclear antigen expressed as the antigen receptors of the started B cells. The antibodies are released and course through the body, authority to antigens. B cells produce memory cells, give future resistance. Cell interceded reaction incorporates, for the most part, by T cells in response to any cell that exhibits variation MHC markers, including cells assaulted by pathogens, tumor cells or transplanted cells. The cell intervened invulnerable response is created without anyone else's input. Cells or APCs demonstrating remote antigens bind to T cells. Interleukins co-strengthens incitation of T cells. If MHC and endogenous antigens are appeared on the plasma layer, T cells increase, making cytotoxic T cells. Cytotoxic T cells obliterate cells demonstrating the antigens. If MHC2 and exogenous antigens are appeared on the plasma layer, T cells duplicate, making right-hand T cells. Assistant T cells release interleukins which stimulate B cells to convey antibodies that scrape to the antigens and quicken non-unequivocal authorities, NK cells and macrophages, to obliterate the antigens. The complement system. The complement, named by Paul Ehrlich, is a course of roughly 30 serum and cell surface proteins or glycoproteins which assume a significant job in both innate and adaptive immune responses. Primary elements of supplement framework are lysis of cells, opsonization, viral balance, incendiary reaction, solubilization, and freedom of resistant complex from the course and store them in spleen and liver. Component of complement. Complement components are assigned by numerals like C1, C2, C9 or letter image, for example, factor D, or by paltry names, for example, homologous limitation factor. Assignment C1, C2, C9 indicates the request wherein the parts were found, rather than their situation in the enactment arrangement. Complement components are integrated for the most part by liver hepatocytes. Furthermore, immense proportions of enhancement fragments are produced by monocytes, tissue macrophages, and epithelial cells of the gastrointestinal tract. In the dissemination, the centralization of all supplement proteins is about 3 mg per milliliter. Some supplement segments are found at high focuses, for example, C3 at about 1 mg/ml, while others, for example, factor D and C2, are found in just follow sums. The functions of complement systems are triggering an enhancement of incendiary responses, the attraction of phagocytes by chemotaxis, clearance of resistant buildings and apoptotic cells, cellular enactment for microbial slaughtering, direct microbial slaughtering, and significant job in the effective advancement of counteracting agent reactions. Figure 4.99 Role of the complement system. Primary capacity of this framework is to name pathogens and other remote bodies for disposal from the host. The complement actuation pathways have developed to fill this need, and the different manners by which enactment can be activated, together with natural enhancement instruments, guarantee proficient acknowledgement and leeway. Additionally, there are a few distinct approaches to initiate the complement framework, so giving a huge level of adaptability accordingly. The principal enactment pathway to be found and named is the classical pathway is started by antibodies bound to the outside of the objective. The subsequent one is an alternative pathway, which gives a neutralizer autonomous component to complement enactment on the pathogen surface. Furthermore, the last one is the lectin pathway. It is most as a late depicted initiation pathway, likewise sidesteps counteracting agent to empower proficient enactment on pathogens. The majority of the over 3 noteworthy pathways of complement framework involve the enactment of C3, which is the most bounteous just as significant to the complement proteins, comprise a proteolytic course wherein edifices of complement proteins make chemicals that separate other complement proteins in an arranged way to make new enzymes, along these lines enhancing and perpetuating the initiation course. Subsequently, a little boost can quickly produce a huge impact. All enactment pathways meet on a typical terminal pathway, a non-enzymatic framework for causing layer disturbance and lytic murdering of pathogens. The invulnerable resistance and neurotic impacts of complement enactment are intervened by the sections and buildings produced during initiation. Why the small chemotactic and pro-inflammatory? Fragments C3a and C5a. Why the large opsonic fragments C3b and C4d. Why the lytic membrane attack complex MAC. Complement pathways. Immunoglobulins, microorganisms, others. Viruses, bacteria, others. Classical immune complexes. Containing IgM, IG1, IG2 or IG3. HIV and other retroviruses, vesicular. Stomatitis virus, mycoplasma, SPP. Polyanions, especially when bound to cations. 3PO4, DNA, lipid A. Cardiolipin, 2SO4, destrin sulfate. Heparin. Chondrogen sulfate, complement pathways. Immunoglobulins, microorganisms, others. Viruses, bacteria, others. Alternative immune complexes. Containing IG, IgR. IG less. Efficient than. Classical. Pathway. Some virus-infected cells like Epstein-Barr virus. Many. Gram-positive N. Negative organisms, trypanosomes, leishmania. SPP, many fungi. Dextran. Sulfate. Heterologous erythrocytes, complex. Carbohydrates, e.g., zymosin. lectin HIV and other retroviruses. Many. Gram-positive N. Negative organisms. Arrays of. Terminal. Mannose. Groups. Acetylated. Sugars. Table 4.22 Complement activation. Nomenclature and ways in which the pathways are controlled. Figure 4.100 Activation of complement pathways. These are mediated by classical, lectin-mediated and the alternative pathway. Molecules. Biologically active. Fragments biological function active in which? Pathway. IgM, Ig binding to pathogen surface and initiating complement cascade. Classical pathway. Mannose binding lectin, orthocolins. Binding to carbohydrates on microbial surface and initiating complement cascade. Lectin pathway. C1 circa 1Q, C1R2. C1's 2. Initiation of the classical pathway by binding Ig. Binding to apoptotic leaves and initiating phagocytosis of apoptotic cells. Serine protease, cleaving C1R and C1s. Serine protease, cleaving C4 and C2. Classical pathway MAS1 MBL associated serine protease 1. MAS2 appears to be functionally the more relevant MAS protease. Lectin pathway. MAS2 serine protease, in. Complex with MBL, the colon and MAS2. Cleave C4 and C2. C2C2 a serine protease. With C1 and C4b, is AC3 convertase. Classical and lectin pathways. C4C2b inactive in complement pathway. Cleavage of C2b by plasmin releases. C2-kinin, a peptide that stimulates. Vasodilation. C4C4b C4a. C4c, C4d. Binds microbial cell membrane via thioester bond. With C1 and C2a, is AC3 convertase. Has weak anaphylotoxin or inflammatory activity. Proteolytic cleavage products are generated by factor I. Molecules. Biologically active. Fragments biological function. Active. In which pathway? C3C3AC3b. C3H2O. IC3b and C3F. Anaphylotoxin. Mediates inflammatory signals via C3AR. Potent inopsonization. Tagging immune complexes. Pathogens in apoptotic cells for phagocytosis with C4b and C2a forms a C5 convertase. With B flat forms a C3 convertase. With B flat and one more molecule of C3b, C3bb3b acts as AC5 convertase. C3 molecule in which internal thioester bond has undergone hydrolysis with B flat acts as a fluid phase C3 convertase. Proteolytic fragments of C3b generated by factor I. IC3b binds receptor CR3, CR4 and CRIG. CR2 binds weakly. Classical pathway. Tickover and properdin. Alternative pathways. Tickover and properdin. Alternative pathways. Alternative pathway C3c and C3d are C3 decigrams. Proteolytic fragments of IC3b generated by factor IC3d for decigram bind Ag into CR2, facilitating Ag binding to B cells. C3c binds CRIG on fixed tissue macrophages. Factor B binds C3H2O and is then cleaved by factor D into two fragments, BA and BB. Alternative pathway. BA smaller fragment of factor D mediated cleavage of factor B. B flat may inhibit proliferation of activated B cells. Larger fragment of factor D mediated cleavage of factor B with C3H2O acts as fluid phase C3 convertase. With C3b acts as cell bound C3 convertase. With two molecules of C3b acts as C5 convertase molecules. Biologically active. Fragments biological functions. Active. In which pathway? Factor D proteolytic enzyme that cleaves factor B. Into BA and B flat only when it is bound to either C3H2O or to C3b. Factor. Properdin P stabilizes the C3bb complex on microbial cell surface. C5C5 anaphylotoxin binding to C5AR induces inflammation. All. C5b component of MAC binds cell membrane and facilitates binding of other components of the MAC component of MAC. All. C6 stabilizes C5b. In the absence of C6, C5b is rapidly degraded component of MAC. All. C7 binds C5b C6 C7 and induces component of MAC. All. C8 binds C5b C6 C7 and creates a small pore in membrane. Component of MAC. All. C91019 molecule. The initiation of the complement by the classical pathway starts with the arrangement of antigen Ag antibody A flat complex or the authoritative of the immunize of the appropriate enormous antigen. For example, a cell with inside of supplement protein. Just surface bound Ig and IgM antibodies can enact supplement, and they do as such by means of this way. The classical pathway is started when C1 ties to the A flat in an Ag A flat complex. C1 is a complex of three unique proteins, C1q, made up of 6 headed recognition units, joined with two molecules each of C1r and C1s, the enzymatic units of the complex. 1. C1 actuation. C1q is the C1 complex that ties through its globular head group to the Fc locales of the immobilized A flat and experiences changes fit as a fiddle that trigger autocatalytic actuation of the enzymatic unit C1r. Activated C1r then cuts C1s at a solitary site in the protein to actuate it. C1 actuation happens just when a few of the 6 head groups of C1q are bound to A flat. Just surfaces that are thickly covered with immune response will triggers the procedure. This constraint diminishes the danger of unseemly actuation on host tissues. Increase in recurrence of actuation of C1 in diminishing request. IgM greater than Ig3 greater than Ig greater than Ig2 greater than Ig4 greater than IgD greater than IgA. Ig don't have C1q receptors, so they can't actuate complement pathway. 2. Cleavage of C4 and C2 by C1's enzyme. C1's enzyme has two substrates, C4 and C2, which are the following two proteins in the classical pathway grouping. C1 separate the inexhaustible plasma protein C4 at a solitary site in the molecule, releasing a little section, C4a, exposing a labile thioester group in a huge piece C4b. Through the profoundly responsive thioester, C4b turns out to be covalently connected to the actuating surface. C4b ties the following segment, C2, in an Mg2 plus dependent complex and presents it for cleavage by C1s in a neighboring C1 complex. The piece C2b is discharged. C2 remains related with C4b superficially. 3. C4b2a is the classical pathway C3 convertase. The complex of C4b and C2a is the following activation enzyme. C2a and the C4b to a complex cuts C3, the richest of the complement proteins, releasing a little piece, C3a, exposing a labile thioester group in the large fragment C3b. 4. C4b2a3b is the classical pathway C5 convertase. Some of the C3b shapes will tie legitimately to C4b2a, and the termolecular complex solidified. C4b to a 3b can tie C5 and present it for cleavage by C2a. A small fragment, C5a, is released. The large fragment, C5b, remains associated with the C4b to a 3b complex. 5. The ability of C4b and C3b to bind surfaces is fundamental to complement function. C3 and C4 are homologous molecules that contain a bizarre auxiliary element, an inside thioester bond between glutamine and a cysteine buildup that, in the flawless particle, is covered inside the protein. When either C3 and C4 are severed by the convertase, a conformational change happens that uncovers the inside thioester security in C3b and C4b, making it entirely flimsy and exceedingly helpless to assault by nucleophiles. For example, hydroxyl groups and amine bunches in layer proteins and carbohydrate. This response makes a covalent bond between the complement part and the ligand, locking C3b and C4b onto the surface. The uncovered thioester stays responsive for just a couple of milliseconds since it is vulnerable to hydrolysis by water. This lability confines the official of C3b and C4b to the quick region of the enacting chemical and averts harm to encompassing structures. 6. Cleavage of C5 is the final enzymatic step in the classical path. C5 convertase starts the official, and cleavage of a disulfide connects heteroimeric protein C5 into C5a and C5b. The littler part, C5a diffuses away, and the bigger section C5b appends to C6 and prompts the development of a membrane attack complex MAC. The C5b, C6, C7, C8 and a number C9 consolidates together to frame the lytic complex, C5678-9N. Figure 4.101 Classical pathway of the complement system. The pathway displays how the classical pathway works in activating the complement system. Alternative pathway. The alternative or propitin pathway of complement actuation additionally gives a autonomous enactment of the supplement on pathogen surfaces. This pathway is in a consistent condition of low-level initiation, known as tick over. This pathway includes 4 serum protein C3, factor B, factor D, factor P or propitin. C3 is hydrolyzed at a moderate rate in plasma, and the item, C3H2O, has a significant number of properties of C3b, including the ability to tie a plasma protein factor B, FB, which is a nearby relative of the classical pathway protein C2. Development of the complex between C3b or C3H2O and FB is Mg2+ dependent, so the elective pathway is inert without Mg2+ ions. C3BBB complex is the C3 convertase of the alternative pathway. C3b or C3H2O FB becomes a substrate for an intrinsically active plasma enzyme termed factor D, FD. FD cuts FB in the C3BB complex, releasing a fragment, bond, while the residual portion, B flat, becomes an active protease. C3BBB complex is the C3 separating enzyme, C3 convertase, of the elective pathway to make more C3 convertase, subsequently shaping a positive criticism intensification circle. Initiation may happen in plasma, all the more effectively, on surfaces. On an activating surface, for example, a bacterial membrane, the enhancement will happen unhampered, and the surface will quickly end up covered with C3b. In a way closely resembling that found in the classical pathway, C3b particles authoritative to the C3 convertase will change the substrate particularity of the complex, creating a C5 separating protein, C3BBB. Cleavage of C5 is the last proteolytic step in the alternative pathway, and the C5b fragment remains associated with the convertase. Figure 4.102 Alternative or propitin pathway of complement activation. Mannan-binding lectin pathway. The lectin varies from the classical style pathway just in the underlying acknowledgement and actuation steps. Undoubtedly, it tends to be contended that the lectin pathway ought not to be viewed as a different pathway, but instead a course for old style pathway actuation that sidesteps the requirement for AB. The C1 complex is supplanted by a fundamentally comparable multimolecular complex, including a C1q-like acknowledgement unit, either mannan-binding lectin MBL or Vicolin, a family of 3 proteins in man, and several MBL-associated serine proteases MASPs. C1q and MBL are individuals from the collection group of proteins portrayed by globular head districts with restricting exercises and long collagenous tail areas with different jobs. The colons are structurally similar, but the head regions comprise fibrinogen-like domains. MBL ties the basic starches mannose and N-acetylglucosamine, while the colons tie acylated sugars and different molecules. These ligands are inexhaustible in cell dividers of assorted pathogens, including microorganisms, yeast, parasites, and infections, making them focuses for lectin pathway enactment. After binding to carbohydrate residues MAS1 and MAS2 bind to MBL. This complex is so formed leads to cleavage and activation of C4 and C2. After inception, it continues through the enactment of C4 and C2 to the liver-initiated proteins of the unpredictable framework. This pathway is progressively similar to the traditional pathway. This pathway is AB-free, so it produces an intrinsic resistant reaction. The lectin pathway is the main method for initiation of the old-style pathway without AB. Apoptotic cells, discharged DNA, mitochondria, and different results of cell harm can straightforwardly tie C1q, activating supplement enactment and supporting the freedom of the dead and biting the dust tissue. Figure 4.103 Mannan-binding lectin pathway of complement activation. Activation of C3 and C5. C3 convertase development is a basic advance in each of the 3 supplement pathways. The C3 convertase divides C3 into 2 pieces, the littler, C3a and the huge section, C3b. C3b proceeds with the supplement enactment course by authoritative to the cell surface around the site of supplement actuation. C3a is a liquid stage anaphylotoxin. Anaphylotoxin is a tie to receptors on pole cells and blood basophils and initiates degranulation, with the arrival of histamine and other dynamic go-betweens. Anaphylotoxin additionally actuates smooth muscle constriction and expanded vascular penetrability. C3b authoritative to each of the 3 supplement pathways permits the following part in the grouping, C5, to tie and be separated. Hence, the C3 convertase with bound C3b is alluded to as C5 convertase. For traditional and lectin pathways, the C5 convertase has the arrangement C4b to a 3b. For the elective pathway, the C5 convertase has the plan C3bb-C3b. The cleavage of C5 produces 2 sections. 1. C5a is discharged into the liquid stage and goes about as powerful anaphylotoxin. 2. C5b ties to the cell surface and structures the core for the official of the terminal supplement segments. Terminal pathway. The terminal segments of the complement falls are C5b, C6, C7, C8, and C9. These parts tie to one another successively to frame the macromolecular structure called membrane attack complex or MAC, the outcome in cell lysis. 3 supplement pathways combine at MAC. This perplexing structure is an enormous channel through the film of the objective cell, empowering particles and little molecules to diffuse uninhibitedly over the layer. MAC arrangement is C6 official to C5b on a cell surface. C7 then ties to C5b and C6 in additions into the external film of the cell. The consequent authoritative of CH to C5b67 results in the complex infiltrating further into the layer of the cell. Ultimately, in the development of MAC is the official and polymerization of C9, a performed like a particle, to the C5b678 complex. C5b678 on the cell layer goes about as a receptor for C9 that ties to C8. Additional C9 molecules cooperate with the C9 particle in the complex to frame polymerized C9 poly C9. This poly C9 frames a transmembrane channel that exasperates the osmotic equilibrium of the cell. Particles go through the channel, and water enters the cell. The cell swells, and the film ends up porous to macromolecules, which at that point escape from the cell. The outcome is blast from opting cell lysis. Figure 4.104 Formation of MAC. Late-stage supplements C5b-C9 tie consecutively to shape a complex on the cell surface. Various C9 parts tie to this complex and polymerize to frame poly C9, making a channel that disturbs the cell membrane. Initiation of supplement results in the creation of a few organically dynamic molecules, which add to the slaughtering of the cell, opsonization, chemotaxis, hypersensitivity, and aggravation. Figure 4.105 Summarized form of 3 complement activation pathways. Biological activation complement component cell lysis C5b-C9. Inflammatory response anaphylotoxin C3a, C4a, C5a opsonization C3b, CHB chemotaxis C3a, C5a viral neutralization C3b, C5b9 immune complex clearance C3b. Table 4.24 Biologically active functions mediated by complement products activity responsible complement component innate defense against infection. Lysis of bacterial and cell membranes. Membrane attack complex C5b-C9. Opsonization covalently bound C3b, C4b induction of inflammation. And chemotaxis by anaphylotoxins. C3a, C4a, C5a anaphylotoxins and the receptors on leukocytes. Interface between innate and adaptive immunity. Augmentation of antibody responses. C3b and C4b and their proteolized fragments bound to immune complexes and antigen, C3 receptors on immune cells. Enhancement of immunologic memory C3b and C4b and their fragments bound to ag and immune complexes, receptors for complement components on follicular dendritic cells. Enhancement of ag presentation. MBL, C1q, C3b, C4b and C5a. Potential effects on T cell C3, C3a, C3b, C5a. Complement in the contraction phase of the immune response. Clearance of immune complexes from tissue C1, C2, C4, covalently bound fragments of C3 and C4. Clearance of apoptotic cells C1q, covalently bound fragments of C3 and C4. Loss of CD46 triggers immune clearance. Induction of regulatory T cells. CD46. Table 4.253 main classes of complement activity in the program of host defense mechanism. Receptors alternative. Names ligand cell surface binding or expressions functions. CR1 CD35 C3b, C4b, C1q, IC3b. Erythrocytes, neutrophils. Clearance of immune. Monocytes, macrophages. Eosinophils, FDCs, B cells and some T cells. Complexes. Enhancement of phagocytosis, regulation of C3 breakdown. CR2 CD21, Epstein. Bar virus. Receptor. C3d, C3 decigrams human, C3b, mouse IC3b B cells and FDCs enhancement of B cell activation. B cell coreceptor. And retention of. C3d tagged immune. Complexes. CR3 CD11b, CD18, MAC-1. IC3b, factor H monocytes, macrophages. Neutrophils, NK cells. Eosinophils, FDCs, T cells. Binding to adhesion molecules on. Leukocytes, facilitates extravasation. IC3b binding enhances opsonization of immune complexes. CR4 CD11c, CD18 IC3b monocytes, macrophages. Neutrophils, dendritic cells, NK cells, T cells. IC3b mediated phagocytosis. CRIG BSIG4 C3b, IC3b, C3c. Fixed tissue macrophages IC3b mediated phagocytosis and inhibition of alternative pathway. C1q RPCD93 C1q, MBL monocytes, neutrophils. Components of innate immune response. Natural C or native immunity gives the early line of defense against life forms. It includes cell and biochemical security instruments that are set up even before illness and are prepared to respond rapidly to pollution. The frameworks of inborn resistance are unequivocal for structures that are fundamental to gatherings of related living beings and may not perceive fine differentiation between microorganisms. The basic portions of inborn invulnerability are 1. Physical and substance limits. For instance, epithelia and antimicrobial engineered mixes made of epithelial surfaces. 2. Phagocytic cells, neutrophils, macrophages, dendritic cells, and natural killer NK cells and other characteristic lymphoid cells. 3. Blood proteins, including people from the enhancement structure different middle people of aggravation. Figure 4.106 innate versus adaptive immunity. Just as protection from illness can be natural, inborn, or gained, the instruments intervening it tends to be correspondingly isolated into inborn, left, and versatile, right, each made out of both cell, lower half, and humoral components, for example, free and serum or body liquids, upper half. Versatile systems, all the more as of late developed, perform huge numbers of their capacities by communicating with the more established natural ones. Mast cells. Mast cells are critical in initiating and looking after aggravation. Produced in the bone marrow, juvenile mast cells are discharged into the circulating blood, where they assume a key job in unfavorably susceptible responses and irritation. Whole cells get separated when they go into tissues from the blood. They have enormous cytoplasmic granules containing histamine. Mast cells are found in tissues like skin, connective tissue, and mucosal epithelial tissue of stomach-related respiratory and genitourinary tracts. Mast cells like basophils assume a significant job in the advancement of sensitivities. Mast cells additionally have a receptor for IgE and have granules in which histamine and serotonin are available. Mast cell age is destined to be inadequate in IL-3. Phagocytes. Phagocytes are bone marrow-decided cells of myeloid origin, including neutrophils, eosinophils, basophils, monocytes, and the creation sort of the monocyte. Phagocytic cells of the invulnerable framework involve pervasively macrophages and neutrophils. These cells address the significant cell effectors of nonspecific host boundary and aggravation. Through their ability to phagocytize outside substances and release cytotoxic and pro-inflammatory center individuals, neutrophils and macrophages shield the body from a wide bunch of pathogens and xenobiotics and expect central employment in the host response to tissue harm. In any case, these phagocytic leukocytes furthermore have tremendous cytotoxic potential. A critical number of the mediators released by phagocytes to verify the host also can hurt conventional tissue. Phagocytic cells, e.g., neutrophils and monocytes, are dug in wellsprings of free radicals. Exactly when sanctioned by reasonable lifts, these cells show stepped augments in oxygen usage that are a direct result of the speedy reduction of oxygen to superoxide by plasma-movie-bound NADPH oxidase. The net result is the landing of a great deal of ROS extracellularly. This system is essential for the ordinary working of the sheltered structure. Phagocytes similarly make nitric oxide, a free extraordinary species. The duties of this radical inhaling, microbicidal works out, and is a purpose behind tissue harm or consistent zones of research. Figure 4.107 The job of free radicals in irritation. Neutrophil. Neutrophils have 90% in coursing blood are additionally called polymorphonuclear neutrophils, PMNs, which structure the huge populace of leukocytes as a result of its sporadic molded course. Life expectancy is around 10 to 12 hours. Granule contains lysozyme, myeloperoxidase defensins, and steacidin and gets recolored at impartial pH with hematoxylin color. They are phagocytic in nature, so they slaughter hurtful microorganisms. Lytic catalysts and bactericidal substances which help in phagocytosis are contained inside essential and auxiliary granules. Ordinarily situated in the flowing blood framework, neutrophils relocate to destinations of disease by means of chemotaxis, and they additionally create an assortment of antimicrobial substances, which have a receptor for CD16-2. Developments of flowing neutrophils into tissues known as extravasation make a few key strides, similar to the cell initially sticking to the vascular endothelium. At that point infiltrates the vascular cellular film, moving out into tissue spaces. Like macrophages, neutrophils are dynamic phagocytic cells. Dendritic cell, cells present in tissues that catch antigen and relocate to the lymph hubs and spleen, where they are especially dynamic in showing the prepared antigen to T cells. Dendritic cells can be gotten from either lymphoid or mononuclear phagocyte lineages. Dendritic cells gain antigen by phagocytosis. The antigen is prepared and develops dendritic cells and present it to TH cells. There's such a significant number of sorts of dendritic cells. For example, in skin, Langerhans dendritic cells; in lung, kidney, liver and heart, interstitial dendritic cells; in lymph nodes, intravegetating dendritic cells; in blood and lymph, veiled cells, monocytes-derived dendritic cells, plasmacytoid-derived dendritic cells. Dendritic cells show class 1, 2 MHC particles, B7 group of co-stimulatory atoms, CD80, CD86 and CD40 molecules on their surfaces. Dendritic cells assume a significant job in natural insusceptible guard and as antigen-introducing cells too. Youthful types of dendritic cells go about as phagocytes and murder remote subs entering the body. On development, dendritic cells leave fringe tissues and move to lymphoid. The fiery procedure includes an intricate arrangement of occasions with countless synthetic go-betweens. Receptive oxygen and nitrogen species, just as hypohalous acids, seem, by all accounts, to be a significant segment of the ordinary working of the incendiary reaction. In any case, tissue harm related to perpetual aggravation is interceded partially by the creation of such responsive species. Macrophage. Macrophages and monocytes are a piece of the mononuclear phagocytic framework. Macrophages are proficient in the way toward doing phagocytosis. Monocytes circle in the blood for about some time, and afterwards, they go into the tissues and get developed and separate into macrophages. Macrophages are enormous in size and complex and have expanded phagocytic capacity than monocytes. Y properties. Y presence of membrane receptors such as complement receptors, Fc gamma receptors, cytokines receptors, and TLRs. Y production of cytokines like TNF alpha, IL-6, IL. 10, IL-12, fibroblast growth factor Y antigen presentation. Y phagocytosis. Following the relocation of monocytes from the blood to different tissues, they experience further separation into an assortment of histological structures, all of which assume a job in phagocytosis, including Y in liver, Kupffer cells. Y in the lung, alveolar macrophages. Y in the white pulp of the spleen, splenic. Macrophages. Y in free-floating and peritoneal fluid, peritoneal. Macrophages. Y in bone, osteoclasts. Y in kidneys, mesangial cells. In the central nervous tissue, microglial cells. Macrophage exercises are operated by cytokines discharged by T helper cells, Th cells, by go-betweens of provocative reactions and by parts of bacterial cell divider. Most intense activator of macrophages is IFN gamma. Inactive macrophages have a larger amount of MHC class II particles. Organs where T cells dwell in present antigens. Dendritic cells are designed as exceptionally strong antigens exhibiting cells. Follicular dendritic cells. These dendritic cells, however, don't emerge in the bone marrow and have an unexpected capacity in comparison to other dendritic cells. They are found in lymph follicles in lymph hubs. They don't speak to class II MHC particles, so they don't work as antigen displaying cells. They express large amounts of restricting receptors for antibodies. Derived dendritic cells. Dendritic cells show class 1, 2 MHC particles, B7 group of costimulatory atoms, CD80, CD86, and CD40 molecules on their surfaces. Dendritic cells assume a significant job in natural insusceptible guard and as antigen-introducing cells too. Youthful types of dendritic cells go about as phagocytes and murder remote substances entering the body. On development, dendritic cells leave fringe tissues and move to lymphoid organs where T cells dwell in present antigens. Dendritic cells are designed as exceptionally strong antigens exhibiting cells. Follicular dendritic cells. These dendritic cells, however, don't emerge in the bone marrow and have an unexpected capacity in comparison to other dendritic cells. They are found in lymph follicles in lymph hubs. They don't speak to class II MHC particles, so they don't work as antigen displaying cells. They express large amounts of restricting receptors for antibodies. Basophil. They comprise about 0.5% minus 1% of white blood cells. Basophils have a unilobe core and are amoeboid phytophil. Their life cycle is of around 8 to 12 days. Granules of basophils take essential stains like methylene blue. Basophils are non-phagocytic granulocytes. They assume a significant job in fiery and hypersensitive reactions. They secrete histamine, serotonin and heparin, leukotrienes, and prostaglandins and have a receptor for IgE. Eosinophil. They establish about 3% minus 4% of white blood cells. Eosinophils have a bilobe core and have coarse granules in the cytoplasm. Life cycle of eosinophils is around 2 weeks. Granules of eosinophils take acidic stains like eosin. Eosinophils are motophagocytic cells and are antiparasitic and antiprotozoal in nature by discharging cationic peptides and responsive oxygen intermediates into the extracellular liquid. They help in the mending of wounds and some hypersensitivity responses. NK cells. Natural killer NK cells express cytotoxicity against a wide assortment of tumor cells and infection-contaminated cells. They establish about 5% minus 10% of lymphocytes in human fringe blood. NK cells don't gain film receptors to recognize B and T cells. NK cells recognize its objective by distinguishing various anomalies on cells like bizarre surface antigens shown by some infected tainted cells or tumor cells. NK cells crush target cells not by phagocytosis but rather by discharging organically strong particles. They take after TC cells in their capacity to wreck tainted cells. For instance, NK cells additionally use perforin and granzymes to murder their objectives. In any case, NK cells vary from TC cells in that they murder focuses in antigen non-explicit way. NK cells are equipped for crushing harmful and infection-contaminated cells without past introduction or contact with the remote antigen. Chiari-Higashi disorder is an autosomal passive ailment related to the absence of NK cells. NK cells perceive focus in 2 ways. They utilize NK cells receptors that can recognize irregularities. For example, low MHCI show in bizarre markers on threatening cells and cells contaminated by some infections. On the opposite, NK cells perceive potential target cells rely upon certain infections in the way that some tumor cells and cells tainted by certain infections showing antigens, against which the invulnerable framework has made a counteracting agent reaction, so antitumor or antiviral antibodies are bound to their surfaces. Since NK cells express film receptor CD16 for the Fc part of the Ig, they can tie to these antibodies and thusly obliterate the focus on cells. This is a case of a procedure known as neutralizer subordinate cell intervene cytotoxicity. Toll-like receptors. Till date, 10 functional TLRs TLR 1 to 10 are reported in humans and 12 in mice TLR 1 -9, 11 -13 that act as prompt responders to danger signals. These TLRs are expressed in various combinations by different subsets of immune and non-immune cell types such as dendritic cells, monocytes, macrophages, neutrophils, B cells, T cells, fibroblasts, endothelial cells, and epithelial cells. Charles Janeway 1989 proposed that cells are capable of recognizing structural shapes or patterns called PAMs expressed on pathogens but not on the host. This led to the identification of the first human pattern recognition receptors following an earlier discovery of toll means great in germinant receptors in the fruit fly Drosophila. Loss of function mutations in toll receptor rendered Drosophila highly susceptible to fungal infections, whereas gain of function mutations led to increased production of certain antifungal proteins suggesting a pivotal role of these receptors in detecting fungal infections as well as initiation of the innate immune response. The amino acid sequence of toll receptors in Drosophila facilitated the identification of toll-like receptor sequences in the Human Genome Project database. Pattern recognition receptors exemplar ligands. Toll-like receptors TLR1, TLR2, TLR6, TLR4, TLR5, TLR3, TLR7, TLR8, TLR9, TLR10. Bacterial lipopeptides LPS, hyaluronan. Bacterial flagellin double-stranded RNA, single-stranded RNA DNA. TLRs 1, 2, 4, 5, and 6 recognize and bind to the components of microbial cell walls and membranes unique to pathogens. The bacterial ligands are well characterized, including LPS and lipoteichoic acid from cell walls, lipoproteins from the cell membrane, and a structural component of bacterial flagella called flagellin. TLRs 3, 7, 8, and 9 are primarily expressed intracellularly on endoplasmic reticulum and endosomal membranes, where they detect microbial nucleic acids, including double and single-stranded RNA from RNA viruses and DNA from most organisms. TLR9 binds to unmethylated CpG motifs present in rejection or autoimmune disease. One of the prominent examples of this type of tissue is the cutaneous-associated lymphoid tissue. Primary lymphoid organs. The immature lymphocytes become immunocompetent by maturing within the primary lymphoid organs following hematopoiesis. The T cells arise within the thymus, and in mammals like humans and mice, the B cells arise in the bone marrow. Thymus. This primary lymphoid organ is the site where T lymphocytes development and maturation take place. Thymus generates and selects a range of host protective T cells. The developing thymocytes generate an enormous diversity of T cell receptors. Some of these T cells are capable of recognizing antigen MHC complex, others may be incapable of recognizing the complex, while there are others that react with combinations of self-antigen MHC complex. To check the dispersion of the last batch of cells mentioned, the thymus would remove them by activating apoptosis or programmed cell death (PCD). About 95% of all thymocytes die by apoptosis in the thymus without ever reaching maturity. We have already discussed in detail the T lymphobiosis that occurs in the thymus. The thymus, a flat bilobed organ, is situated above the heart. Each of the capsule-surrounded lobes are further divided into lobules, which are separated from each other by trabeculate strands of connective tissues. The lobules have 2 compartments. 1, the outer cortex, which is densely packed with immature T cells or thymocytes. 2, the sparsely thymocyte-populated inner medulla. These 2 compartments are crisscrossed by a 3-dimensional stromal cell network comprising epithelial cells, dendritic cells, and macrophages. This forms the framework of the organ and contributes to the growth and maturation of thymocytes. A number of these stromal cells have a physical interaction with thymocytes. In the outer cortex, some of the thymic epithelial cells have long prokaryotic DNA, and TLR8 binds to single-stranded RNA. These TLRs cannot distinguish self-nucleic acids, those of the host cell, on structural differences alone, and recognition of foreign nucleic acids, those of the pathogen, largely depends on location in the cell. The role of TLRs was extensively studied in mice models. One such prototypical example is the mouse model of sepsis, which develops by either injecting mice with bacteria to induce inflammation or injecting isolated bacterial components, such as LPS present in the cell walls of all gram-negative bacteria. Mice with a defective TLR4 protein are completely resistant to LPS-induced sepsis, suggesting that TLR4 is the receptor for LPS and that it generates an innate immune response following LPS stimulation. TLR binding with microbial ligands leads to activation of several signaling pathways and transcription factors, which in turn results in the expression of genes involved in antiviral responses and inflammatory responses. Organs of the immune system. Contributing to the functions of the immune responses are a number of morphologically and functionally diverse organs and tissues, which are termed the lymphoid organs and tissues. These are distinguished into primary and secondary lymphoid organs depending on their functions. Primary lymphoid organs: Y thymus, Y bone marrow. Secondary lymphoid organs: Y lymph nodes, Y spleen, Y MALT or mucosal-associated lymphoid tissues like GALT, gut-associated lymphoid tissue. In addition to these tissues, there are the tertiary lymphoid tissues. These tissues are essentially similar to the secondary lymphoid organs in structure and composition but contain fewer cells. They respond to inflammatory responses during microbial infection, graft membrane extension surrounding as many as 50 thymocytes, forming large multicellular complexes. These are called Nurse cells. There are other cortical epithelial cells, as they traverse the cortex interact with thymocytes and have long interconnecting cytoplasmic extensions that form a network. As it is already clear, the thymus is a site for T-cell lineage cell maturation, and if it goes missing, as in the case of thymectomized mice, there is a drastic decrease of circulating T lymphocytes and consequently an absence of cell-mediated immunity. In human babies with congenital birth defects depicting the DeGeorge syndrome where the thymus fails to develop, there is the absence of circulating T cells, cell-mediated immunity and an increased incidence of infectious diseases. The thymus develops till puberty, and after that, it begins to atrophy with increased accumulation of fat with aging. This leads to lesser T cells in the circulation of aged people, which is a cause of yeast immunity. A thymus in a newborn weighs 70 grams, whereas an elderly weighs only 3 grams. Bone marrow. The bone marrow is the site for B cell development. The immature B cells proliferate and differentiate and interact with cytokine-secreting stromal cells, which leads to their development. A selection process within the bone marrow eliminates any B cell with the potential for self-reaction. Though bone marrow is the site for B cell development for mice and humans, but for birds, the lymphoid organ associated with the gut called the bursa of Fabricius is where B cells mature. In cattle and sheep, the maturation occurs early in the gestation period within the fetal spleen and in the Peyer's patch embedded in the wall of the intestine. Bone marrow is a spongy viscous fluid that fills the inside of the bones and is of two types: one red bone marrow that helps produce blood cells, two yellow bone marrow that helps store fat. There are numerous blood vessels and capillaries in both types of bone marrow and thin vein vascular sinuses that drain into a central vein. The central vein exists in the marrow and drains into the general blood circulation. The red bone marrow works in cooperation with the liver and spleen to get rid of old red blood cells. The early development of hematopoiesis is located in the yolk sac in embryo, then it shifts to the liver, and shortly before birth, hematopoiesis is taken up by bone marrow. In adults, within the vertebrae, hips, ilium, breastbone, sternum, ribs, skull, and at the metaphyseal and epiphyseal ends of the long bones of the arm, humerus, and leg, femur, and tibia, highest concentration of red marrow is observed. The other areas comprising cancellous, or spongy, bones and central cavities of the long bones are filled with yellow marrow. It is within the bone marrow all the cells of the blood are produced from the hematopoietic stem cells, HSCs. As previously discussed, the B cells develop their receptors during different stages of development within the bone marrow. The B cells with IgM plus IgD receptors leave the bone marrow and circulate in the blood. The B cell also undergoes gene rearrangement in the bone marrow, which will be discussed later. Secondary lymphoid organs. To understand the structure, function, and vital purpose of the lymphoid tissues, it is essential to first have an idea of the lymphatic system. Lymphatic system. What is the lymphatic system? In Latin, lympha means water. We can define the lymphatic system as a part of the blood vascular system and an indispensable part of the immune system, which comprises a large network of lymphatic vessels that carry the clear fluid lymph towards the heart. Thoracic duct, which is the largest lymphatic vessel, empties into the left subclavian vein near the heart. There are a series of one-way valves within the lymphatic vessels that ensures that the lymph flows unidirectionally toward the heart. The heart has no part in the flow of the lymph in the lymphatic system. Rather, the movement of the muscles causes squeezing of the lymph vessels, which help in the flow. How does the lymph separate itself from the blood? The idea that defines this separation is that as blood circulates under pressure, the blood plasma seeps through the thin wall of the capillaries into the surrounding tissue. This fluid is called the interstitial fluid, and much of it returns to the blood through capillary membranes. The part that is left is called the lymph, and this drifts from the spaces in connective tissue into a network of tiny open lymphatic capillaries which further flows into progressively large collecting vessels called lymphatic vessels. One job of the lymphatic system is to capture leaking fluid from the blood and return it back to the blood to ensure a steady state level of fluids within the circulatory system. It also serves as a transporter for lymphocytes and antigens from the connective tissues to organized lymphoid tissues, where the lymphocytes interact with invading trapped antigens and undergo activation. These are mature lymphocytes that have been generated in the primary lymphoid organs, which either circulate in the blood or escape into the lymphatic vessels before being returned back to the blood. We can find that various types of organized lymphoid tissues are located along the vessels of the lymphatic system. The two most highly organized secondary lymphoid organs are the lymph nodes and the spleen. They have lymphoid follicles as well as distinct regions of T lymphocytes and B lymphocytes activity and are surrounded by a fibrous capsule. The secondary lymphoid tissues, the mucosal-associated lymphoid tissue, MALT found at various body sites are less organized and include Peyer's patches in the small intestines, the tonsils, appendix, and numerous lymphoid follicles within the lamina propria of the intestines and in the mucous membranes lining the upper airways, bronchi, and genital tract. Lymphoid tissues in the lung and lamina propria of the intestine wall also consist of diffuse collections of macrophages and lymphocytes. Lymph nodes. Lymph nodes are the sites where immune responses are mounted to antigens in the lymph. These are encapsulated bean-shaped structures comprising a reticular network packed with lymphocytes, macrophages, and dendritic cells. Lymph nodes are clustered organized structures present at the junctions of the lymphatic vessels. The lymph brings in antigens, and as they percolate through these nodes, the antigens get trapped by the intrinsic cellular network of phagocytic cells and dendritic cells, follicular and intravegetating. Lymph nodes architecture supports an ideal microenvironment for lymphocytes to encounter and respond to the trapped antigens. A lymph node can be roughly morphologically divided into 3 concentric regions: 1 the cortex, 2 the paracortex, and 3 the medulla. A lymph node can be roughly morphologically divided into 3 concentric regions: 1 the cortex, 2 the paracortex, and 3 the medulla, each supporting a distinct microenvironment. The cortex, it contains lymphocytes and mostly B cells, macrophages, and follicular dendritic cells arranged in primary follicles. Following the antigen challenge, the primary follicle converts to secondary follicles, each containing a germinal center. In children, B cells are deficient, and the cortex, in such cases, lacks primary follicles and germinal centers. The paracortex, just beneath the cortex lies the paracortex. The paracortex is populated largely with T cells and also contains intravegetating dendritic cells that have probably migrated from tissues to the node. These TCs express high levels of MHC class II molecules which are extremely necessary for presenting antigen to T helper cells. An interesting observation in lymph nodes taken from neonatally thymectomized mice show that there are unusually few cells in the paracortical region. In this context, the paracortex is therefore sometimes referred to as a thymus-dependent area, whereas the cortex is a thymus-independent area. The medulla, it is the innermost layer of the lymph node and is more sparsely populated with lymphoid lineage cells. Of those present, many are plasma cells actively secreting antibody molecules. Of these, B cells differentiate into plasma cells secreting IgM and Ig antibodies. Y within 4 to 6 days of antigen challenge, these foci attain maximum size. Y between 4 to 7 days of antigen challenge, a few B cells and T helper cells migrate to the primary follicle region of the cortex. Their further cellular interactions between follicular DCs, B cells and T helper cells take place, which leads to the formation of a secondary follicle consisting of a central germinal center. Y among the plasma cells formed, some move to the medullary areas of the lymph node, while others move to the bone marrow. Y lymph is emptied from the tissues into the subcapsular sinus via numerous afferent lymphatic vessels that pierce the capsule of a lymph node at various sites. Y the incoming lymph percolates slowly inwards into the cortex, paracortex, and medulla in that order. As it passes through these various parts of the lymph nodes, the phagocytic cells and DCs trap bacteria are particulate material like antigen antibody complexes. Y as the lymph leaves the lymph nodes through its single efferent lymphatic vessel, it is now enriched with newly secreted antibodies by the medullary plasma cells. Y there is also a 50-fold higher concentration of lymphocytes in the efferent vessel to afferent lymphatic vessels. The increase is due to the phenomenon of lymphocyte proliferation within the node in response to antigen. But 25% of these lymphocytes are due to blood-borne lymphocytes that migrate into the node by passing between specialized endothelial cells that line the postcapillary venules of the node. Y an actively responding lymph node appears swollen due to a manifold increase in the lymphocyte concentration. Factors released in lymph nodes help in increased migration of these immune cells. Spleen. Spleen is a large, ovoid secondary lymphoid organ situated high in the left abdominal. What happens within these lymph nodes? The foreign antigens are picked up by the lymphatic system and carried to these organized lymphatic tissues, such as the lymph nodes, for trapping the foreign antigens. There are lymphoid tissues that are organized into lymphoid follicle structures. These are comprised of aggregates of lymphoid and non-lymphoid cells that are surrounded by a network of draining lymphatic capillaries. Before activation by an antigen, the lymphoid follicle is called a primary follicle and includes a network of follicular dendritic cells and resting B cells that are small in size. Once the primary follicles are exposed to antigenic challenge, it develops into a large secondary follicle comprising of a ring of concentrically packed B cells surrounding a center called the germinal center. In the germinal center, there is a focus on proliferating B lymphocytes and another area of non-dividing B lymphocytes and some helper T cells interspersed with macrophages and follicular dendritic cells. Most of the antigen-activated B lymphocytes divide and differentiate into antibody-producing plasma cells in the lymphoid follicles, but only a few of them will actually find their way to the germinal center. The ones that reach the germinal center undergo several rounds of cell division and endure gene mutations of the gene that encode their antibodies at an unusually high rate. Following this, only those antibody B cells which have a higher affinity for binding antigens survive compared to weaker counterparts. In this rigorous selection by the germinal center, almost 90% of the B cells are subjected to apoptosis, and those that survive to differentiate into plasma cells or memory cells. Lymph nodes and immunity. Why the antigens carried to various regional nodes by the lymph get trapped, processed and jointly resented with MHC class II molecules by the interdigit DCs, which result in activation of T helper cells. Why the B cells are also likely to get initially activated within the T cell rich paracortex. Why the activated T helper and B cells form small foci consisting largely of proliferating B cells at the edges of the paracortex. Some cavity. The spleen plays a major role in immune responses. It filters blood and traps bloodborne antigens. It responds to systemic infections. It is not supplied by lymphatic vessels, but antigens and lymphocytes in the blood are carried into the spleen via the splenic artery. Higher percentage of recirculating lymphocytes pass through the spleen than through all the lymph nodes combined. The spleen is enclosed by a capsule with an extended number of projections called trabeculae that spread into the interior to form a compartmentalized structure. The compartments are composed of 1, the red pulp, and 2, the white pulp. The red pulp consists of a network of sinusoids populated by macrophages and numerous erythrocytes and a few lymphocytes. It also comprises splenic cords of Billroth. Within the red pulp, there are reticular cells and fibers. The meshwork of reticular cells and reticular fibers are filled with lymphocytes, macrophages, a large number of erythrocytes, plasma cells, DCs, and granulocytes. At this site, the old and defective red blood cells are destroyed and removed here. The macrophages in the red pulp contain engulfed red blood cells or iron pigments from degraded hemoglobin. The endothelium lining the splenic sinuses is fenestrated, formed by extremely long cells. The white pulp consists of lymphatic tissue cords mostly populated by T lymphocytes and surrounding the course of a splenic artery in certain places interrupted by lymphatic nodules, noduli lymphatocyte lineales. White pulp may appear basophilic under the microscope when stained with hematoxylin eosin due to the presence of dense heterochromatin in the nuclei of the numerous lymphocytes. The branches of the splenic artery enter the white pulp through trabeculae and are called central arteries. The central arteries contain capillary networks supplying the white pulp and marginal zone. The penicillin arteries found in the red pulp are extensions of these central arteries into the red pulp. The periarterial lymphatic sheath (PALS) around the central artery is created by the aggregation of lymphocytes, mainly T cells. On the other hand, the lymphatic nodules are formed chiefly by B lymphocytes, and they contain germinal centers developed by the proliferation of B cells following their activation. A point to note is that in humans, the germinal center develops within 24 hours after antigen exposure. These nodules within the spleen are also called Malpighian corpuscles, not to be confused with those of the kidneys. The primary follicles rich in B cells, some of them possessing germinal centers, are attached to the PALS. To the periphery of the PALS is the marginal zone, which is populated by lymphocytes and macrophages. The marginal zone is created on the boundary between white pulp and red pulp. The marginal wall, as already mentioned, has few lymphocytes but numerous active phagocytic macrophages, and the marginal zone is created. It consists of numerous actively phagocytic macrophages but a relatively small number of lymphocytes. Spleen and immunity. Why the bloodborne antigens actually enter through splenic arteries into the marginal zone, where they are trapped by interdigitating DCs, which carry them to the PALS. Why in the sinuses of the marginal zone, the lymphocytes enter and from there migrate to the PALS. B cells and T cells are initially activated in the T cell rich PALS region, as the interdigited DCs capture antigens effectively and present them in a combination of MHC class II molecules to T helper cells. Why the activated T helpers will activate B cells. Why the activated B cells, together with some T helper cells, migrate to primary follicles in the marginal zone. Faced with antigenic challenges, these primary follicles develop into characteristic secondary follicles containing germinal centers as present in the lymph nodes. Why within these germinal centers, the rapidly dividing B cells called centroblasts and plasma cells are surrounded by a dense cluster of concentrically arranged lymphocytes. Why the differentiated and proliferated lymphocytes migrate to the red pulp via the marginal zone through the extensions of central arteries found in the white pulp. Why the memory B cells that also develop in the spleen rapidly activate the secretion of antibodies after exposure to the specific antigen. Why the lifetime of an erythrocyte is 120 days. Within this span of time, the red blood cell is exposed to many adverse effects such as oxidative stress, which lead to its damage and exhaustion. Why also, the shape and elasticity of red blood cells may be compromised, which is otherwise maintained via the cytoskeletal protein in red blood cells called spectrin. Erythrocytes have no inbuilt mechanism to heal themselves. As a result, the damages accumulate and finally render these cells functionless. Why red pulp in the spleen works as a mechanical meshwork, which removes senescent, damaged, or abnormal red blood cells that have lost their shape and elastic properties. Why erythrocytes within the red pulp are broken down by phagocytes, which are in numerous numbers in the red pulp. White circle in case of emergency. The spleen can supply 100 milliliters of blood that is stored within the various venous sinuses and pulp. The release of splenic reserve increases hematocrit by 1-2%, which is caused by the release of many erythrocytes stored in the trabecular meshwork of red pulp. The release of red blood cells is stimulated by increased activity of the sympathetic nervous system, which causes constriction of splenic vessels and subsequent release of red blood cells. Splenectomy affects humans differently at different ages. In children, splenectomy leads to an increased incidence of bacterial sepsis caused primarily by Streptococcus pneumoniae, Neisseria meningitis, and Haemophilus influenzae. Splenectomy in adults has less effect and majorly contributes to some increase in bloodborne bacterial infections. MALT. A group of organized lymphoid tissues defends the total In children, splenectomy leads to an increased incidence of bacterial sepsis caused primarily by Streptococcus pneumoniae, Neisseria meningitis, and Haemophilus influenzae. Splenectomy in adults has less effect and majorly contributes to some increase in bloodborne bacterial infections. MALT. A group of organized lymphoid tissues defends the total pathogen entry vulnerable surfaces of mucous membranes lining the digestive, respiratory, and urogenital systems, which are collectively known as mucosal-associated lymphoid tissue (MALT). These tissues are of varied structures. Some are barely organized clusters of lymphoid cells in the lamina propria of intestinal villi, while others are well organized, such as the tonsils, appendix, as well as the Peyer's patches on the submucosal layer of the intestinal lining. The outer mucosal epithelial layer contains lymphocytes, or more precisely called intraepithelial lymphocytes, IELs. Do you know that the immune system consists of a combined surface area of 400 square meters, which serves as an important entry point for pathogens? If you are baffled, let me give you the answer. It is the total area of the mucous membrane that lines the digestive, respiratory, and urogenital systems. These vulnerable membranes are protected by a collection of lymphoid tissues, which are collectively termed mucosa-associated lymphoid tissue (MALT). These tissues may either display disorganized clusters of lymphoid cells or well-organized structures. The highly organized tissues are readily identifiable tonsils, appendix, and the Peyer's patch, which are present within the submucosa of the intestinal lining. The lamina propria of intestinal villi, on the other hand, is composed of loosely organized clusters of lymphoid cells. These tissues include such a huge number of lymphocytes that it exceeds that of other lymphoid tissues combined. In fact, it is the large population of antibody-producing plasma cells that gives these tissues their functional importance. Plasma cells within MALT are more than the combined number present in the spleen, lymph nodes, and bone marrow. The most well-known MALTs are 1. Gut-associated lymphoid tissue (GALT). 2. Nasopharynx-associated lymphoid tissue (NALT). 3. Bronchus-associated lymphoid tissue (BALT). 4. Conjunctiva-associated lymphoid tissue (CALT). 5. Lacrimal duct-associated LDALT. 6. Larynx-associated LALT, and 7. Salivary duct-associated lymphoid tissue GALT. What does MALT do? Across the mucosal surface of the malt, in response to antigen-specific Th2 response, it produces and secretes IgA. Th1 and cytotoxic T-cell-mediated reactions also occur, but the latter leads to immunotolerance. Figure 4.108 overview of the MALT system. The mucosal-associated lymphoid tissues MALT are divided into inductive and effector sites. Due to the interconnection between both sites, the MALT can protect vast surface areas. MALT can functionally be divided into the inductive site and effector site. Fig 4.108. Within the inductive sites, secondary lymphoid tissues are present where antigen-specific T-cell activation takes place. The other functions that occur are IgA class switching and clonal expansion of B cells. Following T-cell activation and IgA class switching in B cells, they migrate to the effector sites. Since lymphoid tissues are distributed throughout the stretch of the lamina and substantia propria, LL mucosal tissues possess effector sites. At these effector sites, two IgA molecules, secretory IgA, usually joined by HA chain and bound to an epithelial cell membrane receptor, are secreted across the mucosal epithelium. The bound cell membrane receptor acts as a secretory component. MALT and immunity. Why its immunity stems from a large population of antibody-producing plasma cells, whose number is more compared to spleen, lymph nodes, and bone marrow combined. Why MALT produce and secrete IgA across mucosal surfaces in antigen-specific, Th2-dependent reactions. Why reactions such as Th1 and cytotoxic T-cell-mediated reactions also occur, with the latter resulting in immunotolerance. GALT. The lumen of the gastrointestinal tract is outside of the body and is a potential target for pathogenic microorganisms in large numbers. It is prudent for the immune system to have a strong, robust presence in the mucosal layer of the gastrointestinal tract. The tract is heavily 25 kDa-mW, and two heavy chains which are identical, each having 440 amino acid residues and 50 kDa-mW. Each light chain is bound to the heavy chain with the help of covalent disulfide bridges and non-covalent hydrophilic and hydrophobic interactions. The class of the antibody is determined by the type of heavy chains, which are of 5 types and are called isotypes: alpha, gamma, delta, epsilon, micro, and the classes of the antibody are IgA, Ig, IgD, Ig, IgM respectively. Light chains are also of 2 types, lambda and kappa. An immunoglobulin molecule will have either kappa or lambda light chains, but not both together, and similarly is with the heavy chains. Thus, an Ig can be lambda 2 epsilon 2 or kappa 2 epsilon 2. Further, there are 2 subclasses of alpha and gamma heavy chains due to the little variation in the amino acid sequence of their chains. Alpha 1 and alpha 2 of alpha heavy chain and gamma 1, gamma 2, gamma 3, gamma 4 of gamma heavy chains are present in humans. Each light chain and the heavy chain have their C-terminal ends and N-terminal ends. Both the chains have their variable region, variable sequence, and the constant region, constant sequence. The first 110 amino residues of both the chains are highly variable, which varies highly in the antibodies of different specificity. This region of the light chain is called BL, and of the heavy chain is called BH. Further, the light chain has a constant region of about 110 amino acids and is called CL, whereas the constant region of the heavy chain is about 330 to 440 amino acids long and is called CH. The variable regions form the antigen binding site, whereas the biological properties of the molecule or the fate of the antigen bound to the antibody binding site are determined by this constant region. The variable regions in both the chains have some areas which are highly variable in antibodies of the same specificity and are called complementary determining regions, CDR. These CDRs of the BL and BH form the binding site for the antigen. There are some areas in the variable region of both chains which are relatively constant, called framework regions. Loaded with immune-responsive lymphocytes, macrophages, and other cells, this mucosal-associated tissue of the gastrointestinal tract is the best study MALT. It is named GUT-associated lymphoid tissue or GALT. Tertiary lymphoid organs, TLOs. Tertiary lymphoid organs arise due to non-resolving diseases. They are found at the site of chronic infections where there is a long-lasting presence of autoantigens within certain niche territories of peripheral tissues. TLOs are used by the immune system rather than secondary lymphoid organs to counter such disease-causing antigens within or near the antigen-hosting tissues. The cellular constituents of the TLOs are different from those of the secondary organs and have an abundance of macrophages which yields a chronic unyielding inflammatory environment. Apart from these, there are organized accumulations of T and B cells which resemble secondary structures and generate autoreactive effector cells. TLOs can generate and harbor autoreactive and pro-inflammatory, potentially pathogenic lymphocytes but could potentially serve to limit the response by sequestering these or by reducing the magnitude of response. However, whether they contribute to disease pathogenesis or have protective functions is unclear. Antibody, structure and function. Antibodies are the glycoprotein having high specificity to antigens and are synthesized by the B cells. These are also called immunoglobulins, which are located on the B cell membrane as receptors and are also present in the secreted form that is secreted by the plasma cells. These components constitute 20% of total protein components in the blood plasma. Structure of an immunoglobulin. These are the Y-shaped molecules which have 4 polypeptide chains. This heterodimer consists of 2 light chains which are identical, each having 220 amino acid residues and Figure 4.109 structure of an immunoglobulin. A heterodimer consisting of 2 heavy chains and 2 light chains forms the Y-shaped molecule. Light chains have 1 variable domain and 1 constant domain each, whereas heavy chains have 1 variable domain each and 3 constant domains each. Structural analysis of immunoglobulin. Various chemical and enzymatic methods were done by Porter and Edelman to deduce the antibody structure as described. Papain digestion. The antibody Ig was briefly digested with the enzyme papain, a proteolytic enzyme, and it was found that 3 fragments were produced. 2 out of 3 were identical, each having a molecular weight of 45 kDa, whereas third fragment was different and had a 50 kDa molecular weight. The 2 identical fragments showed the antigen binding activity, and therefore these fragments were called Fab fragments fragment, antigen binding, whereas the third fragment did not show any antigen binding activity and was crystallized during the cold storage and therefore was called FC fragment crystallization. Pepsin digestion. The antibody was